So in this lesson, we're going to look at gravitational potential energy, which is a specific type of potential energy. And if we recall, potential energy is defined as an object's ability to do work because of its position or arrangements of parts. So essentially, it's stored energy that will later be released. Therefore, when an object, if raised to a height in the presence of gravity, possesses gravitational potential energy. So the higher an object, the higher its gravitational potential energy. So when we're looking at problems relating to gravitational potential energy, we want to calculate how much work is required to lift something to a certain height above the Earth's surface. So we're going to derive this equation. We know that work is equal to the dot product of force and displacement. Okay, so in this case, you don't really have an angle. So you know that cos of 0 is going to be 1. So this is just 1. And so you're left with work is equal to force times your displacement. And also, as an aside, you know that your force in this case, because we're dealing with gravity, and it's a vertical motion that's happening, is equal to your gravitational force, which is equal to your mass times gravity. We also know that your displacement is equal to height, because you're just dealing with a vertical amount, like vertical distance. So force is equal to mass times gravity, and then displacement is height. We also know that energy is the ability to do work, so they're essentially interchangeable here. So your gravitational potential energy is equal to your mass times gravity times height. And you know that your acceleration of gravity is 9.8 meters per second squared. So just like everything in this course, we want to determine the change of energy, or the delta Eg. And we can determine the change in gravitational potential energy with reference to a starting height by subtracting the initial gravitational potential from the final gravitational potential. So your work would be your final minus your initial gravitational potential energy. And as you can see, this is dependent on height. Okay, example time. A drop tower gondola and its passengers have a combined mass of 500 kilograms. What is the change in their gravitational potential energy when they are raised to a height of 48 meters above the base of the tower? So first thing, let's write out our givens. So I've just labeled the base of the tower is going to be your initial height, and that's going to be 0. So that's our reference point. So your final height is going to be your 48 meters. And this is total mass, and G is always relevant in these kind of situations, so 9.8 meters per second squared. So using the equation we just derived, we know the change in gravitational potential energy is going to be your final gravitational potential energy minus your initial gravitational potential energy. And you know your initial height is 0, so this is 0. And so we can just plug in our values. Our mass is 500. Gravity is 9.8 meters per second squared. And our final height is 48 meters. And that comes out to 235,200 joules. Okay, so now let's talk about conservation of energy. We know that energy can never be created or destroyed, but it can change from one form to another. So in our case, within this unit, we're going to be looking at energy changing from kinetic energy to potential energy, and potential energy back to kinetic energy. But the amount of energy in the total system is going to be constant. For the purpose of this course, we'll only be dealing with isolated systems. So an isolated system is when the total energy of the system is constant and no energy leaves or enters. Therefore, the initial energy of a system must always be equal to the final energy of the system. This means that when presented with problems involving the transformation of energy from one form to another, we must take stock of the initial energy of the system and the final energy of the system. Okay, let's do another example. A 5 kilogram object is dropped from a height and it has a speed of 14 meters per second just before it hits the ground. Using conservation of energy, determine the height that the object was dropped from. So let's write down our givens. Okay, so all we have right now is our mass, our initial velocity, which is starting from rest at the top of the cliff, so it's 0, and our final velocity before it hits the ground is 14 meters per second. So because of the conservation of energy, we know that your initial energy is going to equal your final energy. So let's talk about the type of energy that's happening in each situation. So initially, it's just being held at a height. So it's all potential energy. So we're going to be using our gravitational potential energy equation for initial. And then as it's coming down, right before it hits the ground, it's going to be all kinetic. And so we can make these equal because of conservation of energy. And you know it's going to be final minus initial, so this is final, as your initial is going to be 0. Okay, now solving this, we actually did not need our mass because they were going to cancel out. And we want to solve for height. So that's just half v squared divided by gravity. And we can sub in our values. And that gives us 10 meters. So therefore the object is dropped from a height of 10 meters.